we're going to define power, and we're going to define the relationships between power and work and time and energy and force and velocity, angle, and all that. And we're going to talk about what units we use to measure power in. And so let's define power. I mean, we use definition. Okay. I mean, we use power in everyday language, and usually somebody's really powerful, you know, they can lift a lot of weight real fast, and you know, or whatever, and that's kind of the intuitive sense of what power is. It works, but physics, as usual, physics is a very specific way of defining what we mean when we say power. And power is the rate at which work is done or energy is transferred. The rate at which work is done or energy is transferred. Now, I give this more general definition, energy is transferred, because I want you to know that there are other forms of power that we're not going to talk about. Like when heat flows from a high temperature to a low temperature, you have energy flowing. If you take the amount of energy that flowed, divide it by the time it took to flow, that would be how much, what power, that would be a measure of power. Also, if you have an electric circuit, you have current flowing through an electric circuit, that is a transfer of energy through an electric field and flowing charge in a wire. And sometimes you might have an amplifier or some other, like a toaster oven or something like that, that uses a certain amount of power, like a television set or whatever. They use power, and that's electrical power, and we are going to study electrical power. But for this unit, when we're dealing with mainly with mechanical energy and a little bit of thermal energy, if there's frictions doing work and so on, we're mainly going to deal with work. Like it's the rate at which work is done. Remember that work is a transfer of energy from one system into another system through the application of a force. Okay, so now, so let's go ahead and define that. Power is, well, we're going to use a capital P to represent power. Now, next week, we're going to be using a lowercase p to represent momentum. Okay, so make sure you use capital P for power and lowercase p for momentum. We'll get to momentum later on, but it has to be a capital P. And we say that it's equal to the work done. And it's the rate at which work, and by rate here we mean time. So it's the work done per unit time. You take the total work done, divide it by the time it took you to do that work, and that'll be your average power. Now, let's think about this in terms of units. Well, work is measured in joules, and time is measured in seconds. And so a joule per second, now how many joules are you transferring per second? Well, that is, that's called a watt. Okay, I think named after James Watt or something. He made some important inventions or whatever. But now we use the letter W to abbreviate a watt. Okay, now that's kind of unfortunate because we use W, capital W, to represent work. Now, how do you know when a W means work, or when a W means a watt? Well, if you have, work equals force times displacement times the cosine of the angle between it, oh, this is a variable. This is a variable. When we're using variables, a capital W is representing a quantity called work. But if you see, the power equals, 512, if you see a W like that, well, this is a measurement, and this is what we're measuring. We're measuring power in watts. So if it's with a number, if it's right after a number like this, you're dealing with a unit. Units describe what the number is representing. Okay. Well, look, now actually let's move ahead a little bit. We've got, we said power equals work over time. Well, work is force times displacement times the cosine of the angle. And we're going to divide that by time. We'll call it delta t. Well, this gives us something kind of interesting. What does delta x over delta t equal to? No. Yeah. It's velocity, or average velocity. Delta x over delta t is average velocity. So what this gives is average power. Power equals the force times the average velocity, I'll just write it as v, times the cosine of the angle between the force vector and the velocity vector. So sometimes you'll say, power equals work over time, and sometimes power equals force times velocity. And, you can use either equation to figure out what to do. So, these are the basic equations that we're going to be using to solve these problems. So add these to your equation list. And let's do a real simple example problem here. Before we get to the example problem. Now, we use watts, as I said, but we also use another unit for power that I'm sure you've all heard of. Have you heard of a horsepower? Yeah. 1 horsepower. Now, horsepower is kind of like, okay, I guess they hooked up the average horse, and they figured out how much work it did in a certain amount of time, and they came up with horsepower. I don't know the origins of horsepower. That would be kind of an interesting question. But we don't really want to use horsepower. We want to use watts. So, hey Siri, how many watts in 1 horsepower?
1 horsepower converts to 746 watts.
Oh, 746 watts. Okay, so this is a conversion factor between horsepower and watts. So you're going to get, a watt is a very small amount of power, and but sometimes you want horsepower. Like what's a good car? A car has what? Like if you have a muscle car, who knows? Anybody into cars here? 3 horsepower? 400 horsepower?
There you go.
Huh?
It depends on what car.
I know. Let's say 300 horsepower, right? So you go 300 horsepower. Yikes. Well, if you want to use the metric system, you would say, well, 1 horsepower equals 746 watts. So you get your calculator, and of course I don't have my calculator out right here. Oh yeah, I do. So I'm too lazy to do it. 300 times 746 equals a lot. Equals 23800 watts. Well, we probably wouldn't express it like that. If you're going to deal with in the metric system, we would call this 224 kilowatts. So we quite often use kilowatts instead of horsepower, because you see they're kind of close, aren't they? So if you're dealing with power plants, how much power are they putting out? Megawatts. Or a big, huge nuclear power plant? Gigawatts. And that's what Elon Musk is building out in the middle of the desert, a gigafactory. Because it's going to make gigawatts worth of solar and battery storage and all that kind of crazy stuff. Yeah, gigawatts. There's terawatts. Tera is trillion. Anyway, hey, use this to solve the problems. There are some examples to do that you already did, I think. Anyway, that is all.